Fine students, so in this video I'm going to be looking at this idea of absolute and apparent magnitudes, and this is a scale, a different type of scale that depends on the luminosity and the distance from the star, something that was developed a long time ago and has been amplified in recent times. So I've got a diagram here that hopefully will help us to explain it in more detail. We'll see if we can explain it. So imagine that this is a few of the stars in the night sky, and here I have got the Earth. And when one looks out at the night sky, depending on the size and the luminosity and the nearness of the stars will look at different brightnesses. And from ancient times, a scale or a way of developing it has been developed of labeling or classifying these stars, and it's called the apparent magnitude. And the apparent magnitude is basically an indication or a measure of how bright a star is when viewed from the Earth. So, for instance, this star over here, this would be a big star. This one over here be a relatively big star. This could have an apparent magnitude. We use the small letter m of, say, 1, where this one over here, which is further away, wouldn't look so bright on the Earth, and that would have, say, an apparent magnitude of, say, 4. Now one notices here that we're on a scale here, but as you go bigger, it actually is dimmer. This one over here, a very dim star here, may have an apparent magnitude of about 8. In fact, you probably wouldn't be able to see that star with the naked eye. This star over here, big star, but far away, may have an apparent magnitude of, say, 6, because it's further in. And we know that the amount of light reaching us is proportional to the inverse of the square of the distance. So this apparent magnitude works something like this. We have got a scale, and I'm just going to use from 1 to 6 because basically from 1 to 6 is basically the stars that can be seen with the naked eye. And what it was this star number 1 would be 100 times brighter than star 6, the star over here. So star 1 is 100 times brighter than star 6. So as we can see, we've actually got 5 magnitudes here, 5 increase in magnitudes. So if you take 100, if we say take x to the 5 is equal to 100, where x is the ratio that we actually dividing by, or if we're going this way, we're actually multiplying by. We get a ratio of about x is equal to 2.5. So as you go from star 6 to star 5, it actually becomes times 2.5 times brighter, and the same with 5 to 4, 4 to 1, 3 to 2, and you can go further because you can go into the minus scale. So each time here, star of apparent magnitude of 0, it would be 2.5 times brighter than 1, star of 1. The sun is something like minus 26, and stars that can just be seen with a telescope go on here. So it's a bit of a reverse logic here. As they're getting bigger, the stars are actually getting dimmer. Now, obviously, it's quite difficult to compare this because, like we have in this situation over here, we have a very bright star, but because it's much further away than, say, this star over here, this may have like an apparent magnitude of, say, 3. It may look brighter to the Earth than this star over here. In fact, this star is much bigger. So a way of bringing this all together and being able to really compare stars according to their apparent magnitude was developed. And to do this, I'm just going to draw another circle. I think I need to just erase, do a little bit of erasing here, just to clear this out here. And what they did here was they decided that, and I'm just going to draw on another circle here. Alright, so they decided to compare stars from a distance of 10 parsecs. So if this is a distance of 10 parsecs, then what they would do here is they would bring all the stars to this 10 parsec line. All of them that move in. So obviously these stars over here, which seemed dimmer, actually would become brighter. These stars that were close by would actually become dimmer. And this is called the absolute magnitude. Absolute magnitude. It's given a symbol of capital M. That's an M, if you can believe that. Capital M. And basically, it's the apparent brightness of a star if the star is 10 parsecs away from the Earth. So it's a way of comparing stars. So if all the stars are looked at as if they're from 10 parsecs away, then you can actually compare them. You can actually say, well, that star has got a higher luminosity than that star, because when you look at the absolute magnitude, it tells you the value. And there's a formula that we have for this, and the formula, if I get it right, is m minus capital M is equal to 5 the log of d over 10, where this is the distance that the star is away in parsecs. So that's distance in parsecs. So you have to be quite good at being able to change this formula around, because if I change this around, I can put that over 5. I cross that out. I change into my exponential form, which equal 10 m minus m over 5 is equal to d over 10 is equal to, and I'll just bring this down here. So d, the distance in parsecs, is 10 times 10 to the m minus m over 5, like that. So in that way you can actually work out the distance that the star is away when looking at its apparent magnitude and its absolute magnitude. Alright, so important that you understand this whole idea of a star of apparent magnitude 1 is 100 times brighter than a star that is in apparent magnitude of 6, that there's this 2.5 factor as you go from one order of magnitude to the next. So from 5 to 6 you're actually getting dimmer by 2.5. Go from 6 to 5 you're getting brighter by a factor of 2.5. And then the idea that the absolute magnitude is the apparent magnitude of a star when it is placed 10 parsecs away from the Earth. Okay, thank you very much.